Please take it away.
Great, thanks. So yeah, so this is a result with a lot of moving parts, and we have a very broad audience. So feel free to interrupt with questions and such to hopefully kind of get at the various pieces here. So okay, so first, I'd like to motivate why we should care about these asymptotic fault tolerance results. You might ask, like, okay, well, all these major fault tolerance threshold theorems were kind of well established in the 90s. Like, you know, what's left? And personally, I think it's kind of an interesting fundamental question about like what's the lowest possible overhead of fault tolerance, and I'll define what I mean by fault tolerance momentarily. And I think the other thing that it kind of tells us is what, you know, a fault tolerant, it guides how a fault tolerant quantum computer might look like in the future. So we can take these pieces of like these like asymptotic constructions, and then hopefully use some of these in practice, suitably de-optimized from the asymptotic regime. And then also, there's kind of a need in complexity theory for fault tolerance, and especially like much more sophisticated and stronger fault tolerance results than we have currently today. So what we're going to be looking at is threshold theorems. So the general idea is that we're going to start with a circuit, some depth and some width, and our threshold theorem is going to tell us how to map this to a new circuit of some new depth and some new width that even in the presence of some noise with some maximum rate outputs the same the same output distribution up to some small error. And what I'm going to be talking about is this width blowup and then the depth blowup. So this is just the number, how many more qubits do I need, and then how much deeper is my circuit. So there's a long history of such threshold theorems going back, again, all the way to the 90s. And the thing I want to highlight here is the following. So kind of initially people established these threshold theorems using these like concatenated code schemes. So these are often what's like taught in classes on quantum information or quantum computing. And these kind of proceeded using like not very sophisticated techniques, and just kind of you establish some result against like you can correct one error and then you kind of recursively apply the construction. And then kind of over the last 25 years, we've started to see like some new threshold theorems that are using different techniques. So in particular, these like quantum low density parity check codes, which I'll define in a moment. And these were kind of first used to achieve kind of this space overhead that's like constant. And then you can ask, okay, well, in this constant space regime, how much depth flow do I have? And what we can now show is that actually we can get this depth flow up all the way up to log of 1 plus lim low of 1. And to do it, we actually need something a little bit stronger than a low density parity check code. This is a quantum locally testable code. And I'll tell you how we use that towards the end of the talk. And yeah, so then for the rest of the talk, I'll mostly I'll state the model, and then I'll sketch roughly the interesting bits and pieces of our proof. And so you should think of this circuit M as being Clifford plus T, or in our case, Clifford plus CCZ. And it's not too difficult to convert back and forth as long as you're not asking for very low depth circuits. And then I'm also going to restrict such that the depth. So this is the key parameter here. This is the volume, like the number of gates in my circuit. And I'm going to restrict that my circuit isn't like pathologically deep or anything like that, because that's going to cause some problems. And then I'm glossing over some differences in the classical computation model between these different results, just for simplicity. Okay, so we're going to consider a circuit on qubits composed of Clifford plus CCZ. And we're just doing this to avoid some overheads associated with like unitary synthesis, just for simplicity. And then I'm going to have noisy quantum operations. It's going to have noisy gates. And you can think of it as I'm going to have a layer of quantum gates, constant depth. And then I'm going to permit myself some small amount of classical noiseless classical computation of some depth that's still low depth, but slightly super constant. And I'm going to assume it's perfect. And then we have the stated result. And then we can modify this to get, there exists a straightforward modification to reduce this all the way down to the constant. And you'll hear a little bit about that in the next talk with Quinn. Roughly the overall outline, it looks something like this. And if you're ever lost, this will be in the top right corner at all times. So I'm going to tell you about the code that we're using. So we're going to encode the qubits of the computation into some code, and we call this the computational code. It will be actually a quantum locally testable code. Then we're going to have to construct a single shot decoder for this. So this is a decoder that can process a single round of syndrome extraction and maintain a memory. And then we're going to build up kind of a simple gate set, which is just like gates that we apply kind of component-wise. So these are so-called transversal gates. And then we're going to do something really funny. We're going to start to build up a more complicated gate set of just Clifford gates. And we're going to do this by essentially state distillation. And then we're going to use that to build up like a CCZ gate. And then together that's going to give us the universal computation that we'll use to assemble the main result. So, okay. So the computational code, it's going to be a qLDPC code. And all that is that it's code defined by these two binary check matrices, X and Z. It's CSS. And each row so the columns of this correspond to qubits, and the rows correspond to a stabilizer generator of our code. And so, for example, this bottom row here corresponds to this operator here. So the code is the simultaneous +1 eigenspace of sort of all the operators that are all the stabilizer generators in the Z basis for this matrix and in the X basis in this matrix. And so this qLDPC property is really convenient for us because this automatically gives us fault-tolerant syndrome extraction. So this is just to measure the eigenvalues of all the stabilizer generators that define our code. So the syndrome extraction circuit is going to look something like this. We're going to have a plus state. We're going to do a controlled, we're going to apply control for whatever the operator is that we want to measure. And then we're going to measure in the X basis. And we can do this for all the stabilizer generators in constant depth because these check matrices are sparse. And the way we do it is there's an equivalent, this matrix here, I can think of it as the biadjacency matrix of a graph. So I can associate a graph to this matrix called the Tanner graph. And I just compute the scheduling of which gates to apply to which qubits just by edge coloring the graph. And I can do this efficiently, no problem, because this is a bipartite graph. If I do it just for the Z checks and then just for the X checks. And that's a constant depth syndrome extraction circuit. So the main gadget that I'm going to be doing kind of at all times, you can kind of think of it as going in the background, is I'm just going to be running the syndrome extraction circuit, and then I'm going to decode this syndrome, and I'll say about that in a moment. Okay, so we need something stronger, actually. It's going to be a quantum locally testable code. And what you can think about these locally testable codes, roughly the property is that so this is the syndrome. So in this particular basis that we've picked of stabilizer generators, we can consider the Hamming weight of the bit string that we get out. And all we're saying is that the further you are from a valid code state, the larger the syndrome weight is. And so roughly, so I've plotted here the syndrome weight and the distance from the code space. And we have this upper bound just from the fact that our check matrices are sparse. So kind of the syndrome weight lives below this line. And then for a generic qLDPC code, something that's not locally testable, we can be very far from the code space and actually have a very low weight syndrome. And For the local testability, this is a much stronger property, and what it's saying is that your syndrome, the syndrome weight lives in this cone. Sort of as you step further and further out from a valid code state, your syndrome weight gets bigger and bigger, and this is going to allow you to kind of approximately test if you have like a particularly damaged state or not. And the thing that we're going to need is a decoder for these states with noise attached to them, or if noise added to them. And we're going to need what we call a single-shot decoder. So recall that we had this syndrome extraction circuit. It just measured, and it's going to have faults. So there's going to be some measurement error associated with the syndrome extraction circuit, and there's going to be some input error. And as long as these two are not too large, then we have some control over the output error after we've run our decoder and applied the correction that it outputs. And the output error is kind of controlled by the amount of measurement error that we had. So kind of as long as we're not too far outside the code space, we can correct and bring ourselves back to the code space. In particular, we know of quantum locally testable codes by Dinner, Lin, and Vidic that achieve almost optimal parameters, and we use this fact in our proof. So in particular, the distance and the soundness are kind of off from the optimal, but this is constant by like polylogarithmic factors, and this shows up as polylog-log factors in our proof. So that's kind of one thing that's hiding in the little o of 1. So okay, so the first theorem that we established is that there exists kind of a greedy like bit flipping decoder for these code families that like decodes against like adversarial noise up to this decoding radius, and it has kind of well-controlled residual error. And you'll note here that if I have constant error, you might be like, oh, if I have constant error, then the average weight of that I'm going to get is linear, and this is slightly sublinear. That's not a problem. What we can do is we can do a process that I call threshold amplification, and I'll talk about that at the very, very end. But don't be worried about this fact. Kind of we can reduce the stochastic noise to adversarial noise.
What's the alphabet size?
Binary alphabet, so no problem. There will be larger alphabets later. Great. Okay. Okay. So I've told you how we're going to get like the identity gate, logical identity. We can now correct errors using this kind of funny code. Now we need to sort of build up our gate set, and that's roughly what's going to go on for quite a while. So first off, our codes are qLDPC, which we use to build this error correction gadget that had kind of no spacetime blow up, and that gives us the identity. And then because this is a stabilizer code, we can perform arbitrary logical poly operations. And then if it's CSS, then we get X and Z basis measurements, where we just measure out the full register and infer the result of X or Z basis logical measurement. And then we also get the transversal C0. And this suffices to do a teleportation circuit. So if I just, so this is kind of the standard teleportation circuit that most people see. I have some Bell state, and if I consume it in this way, then I get up to a correction. I get this this unitary gate applied to my input state. And so in particular, if this unitary U is Clifford, then this fix-up is a poly fix-up. And actually, I can do every gate in this circuit, assuming that I have access to this resource state. I can do everything in the circuit with just this gate set here. And so that's what I'm going to do, at least to do the Clifford operations. The other thing that we'll do later is we'll need to do like a CCZ gate, and then we'll have a Clifford fix-up. So we'll kind of bootstrap our way up. Yeah. Okay, so the gate set's kind of funny because the problem is that whenever we're encoding, many logical qubits into a register, there's this question of how do we target? How do we, say, do a gate acting on the second qubit and the fifth qubit, that's like a CNOT or something like that. So there's this issue of how many bits of addressing do we get. So we're going to use this funny gate set here. What's going to be important, what's going to be important is that that this gate set is very small sized, because we're going to prepare many resource states at once that are going to, and we're going to amortize the cost of preparing these resource states. So the gate set itself is just kind of Clifford gates and a third level gate acting on like the first few qubits. And then what we're going to do is we're going to combine them with these two funny gates here that are going to allow us to actually target where when you combine these gates with these gates, that gives us full universal computation. So this last gate here, what I call rotation or rot, just shifts, cyclically permutes the qubits in the register, and we can just do it by like powers of 2. So for simplicity, assume that k is a power of 2. That doesn't cost us much. And then, yeah, for reasons that'll be apparent later, we need this to be logarithmically sized, which this is. The swap gate is just given 2 registers, we just swap the first qubit. Okay. So now, given that, the high-level strategy is going to be something as follows. I'll tell you later how I do this, but we're going to prepare and consume these like resource states. And we're just going to make an arbitrary assignment of, so here I have the circuit that I'm trying to simulate, and I'm just going to make an arbitrary assignment of the qubits to these like registers of like roughly logarithmic size. And then this circuit itself has layers of gates, and we need to schedule the order in which we do that. So roughly it looks something like this, where we have a multigraph where each edge represents a gate that we want to schedule, and then each vertex is the register. So we can do the scheduling, again, with an edge coloring. Looks something like this. So we perform all the gates corresponding to edges of a single color at once. And then so this is like a serialization cost. So we only know how to do, with our gate set, we only know how to perform one gate at once. And so we have to do this serialization. And roughly that's going to give us this like log time overhead, which is the main overhead in our construction. And then for reasons that will be apparent later, we actually have to do a little bit more serialization because our magic state distillation isn't quite what you might hope for, I guess. It's a little bit suboptimal, but overall, this is the main time overhead, is just this serialization. And then the rest will all be log-log. It'll be kind of sub-logarithmic. Okay, so now I just have to tell you how I'm going to prepare these resource states, which is where most of the work actually is. We're
had optimal LTCs when the overhead disappeared.
Good. So not quite. Really, our bottleneck right now is so okay. So you can ask like what's in this little one here. Right now, so we have various polyloglog factors. Some of those are coming from the lack of a good qLTC, but actually the majority of our overhead is actually coming from this magic state distillation here. You might hope, and I think it's actually should be fairly reasonable to achieve, is just log V up to like O tilde log V of the volume. I think that's very reasonable. But yeah, this is okay. So to prepare our resource states, we're going to do distillation. And for those of you that haven't seen state distillation before, roughly what we're going to do is we're going to have some resource state that we want to prepare. And we're going to take in some number of noisy copies of this thing, and we're going to consume them and output some less noisy copies. And you should think of this as happening on logical level of the computational code. So this is being implemented with, for example, these transversal gates. Okay, so given a code that supports a particular transversal gate, that's going to give us a distillation protocol for the resource state that implements that transversal gate. And so what we're going to do is we're going to repeat this distillation protocol, and it looks something like this, where we start with the noisy version of our resource state. We're going to project it onto the code space of this code with the transversal gate, and we're going to apply an error correction operation. And then we're going to have something encoded into that code. And then we're just going to unencode it from the code that we use for distillation, and that's going to give us the copies of these resource states. And in particular, there's this constant rate code family of concatenated quantum Hamming codes. Kind of, it's this really nice trick where you pick a sequence of codes to concatenate where the rate approaches 1. And so in the sequence, kind of the rate of the overall code family approaches a constant. And so that's going to give us the full Clifford group, or distillation protocols for the full Clifford group. And furthermore, because of the concatenated code structure, we can do this unencoding step in low depth. So it's actually quite important that this is a concatenated code family. So okay, so that gives us the resource states for Cliffords with this constant space overhead, and then this depth, this low depth. And so kind of the product of these things is the space-time overhead. Oh, and we also use this to prepare the initial states for our computation. If you're careful, you can avoid using any insulas in the operation of this circuit. And so we can yes. So yeah, you can use this just to prepare even the initial states, which is something that's actually quite subtle to do otherwise. Okay, so, yes.
Just want to make sure I understand correctly. So the states that's being distilled here and later used in teleportation, this is, a single qubit H or S gate at a time, right?
That's right. Yeah. So in some cases, for example, the rotation state, or the resource state for rotation, it's actually going to implement like a full permutation. It's still, so what we require is that this unitary U is actually implementable by a constant depth circuit. It's kind of a technical requirement, which this resource state is. It's just a bunch of bell pairs that are kind of connecting the different coordinates up.
That's for the rotation.
That's for the rotation. That's right. Yeah.
But like in general, these Clifford gates that you're mentioning here are single qubit H, S, and some specific C nodes.
That's right. Yeah. Okay. Any questions so far? Okay. Cool. So now I need to tell you about how we get magic states, and this is the part where our main overhead comes from, like beyond the logarithmic part. And roughly, kind of the issue is that we have to count the space-time cost, which is the gate count over the number of magic states that are output. And so quite commonly, this ends up being some logarithm to some power in the output error rate. And kind of what's been known for qubits up until middle of last year was kind of a constant factor. And so that would directly translate to a superlinear power of log of the circuit size. So it'd be like, we'd have like log 1.68 or something like this. The issue is how can we get below that? And so one simple construction that works is using these punctured quantum Reed-Solomon codes over a qubits of dimension 2 to the m. And the idea will be is that we'll grow the code size that we use in each level of distillation, and that's going to give us the sub-logarithmic space-time cost. So, okay, we can write down some theorem, which is roughly that there exists good CSS codes over this alphabet that's an extension field, and with good parameters. And this is a generalization of a work of Krishna and Tillich, who did this for prime size alphabet. And the usage of the extension fields is actually quite important because this allows you to convert back to qubits. For just generic, say like seven-dimensional qubits, for example, it'd be quite difficult to relate them back to the initial qubits, for which you need the magic states for. So what this extension field structure allows us to do is actually to simulate these qubits with our qubits. So in particular, if I have an element in this extension field, I can write the element in terms of coefficients that are in the base field times some element in the extension field. So if I have my qdit, I can write its state in terms of its expansion in terms of the coefficient. And so what I'm going to do is I'm going to simulate these qubits with the qubits, and I'm going to distill this state as like an intermediate thing. And then I'm going to use Clifford operations to convert this back to the qubit CCZ state. And I can do this without losing too much in my parameters. And this is going to allow us to get the sub-logarithmic distillation cost. So that's so this is kind of one simple way to get this the sub-logarithmic distillation protocol. There's also, at least if you only care about the ratio of input to output magic states, you can get this all the way to a constant using these fancy constructions of, like, for example, algebraic geometry codes that Louis and Quinn and Adam Wills have shown. But unfortunately for us, you really need there's this cost of the decoding circuit that has to be quite low in order to not harm the overall overhead of our scheme. So finally, I have to tell you how I'm going to prepare these input states, these noisy input states, for the state distillation. And this is where I'm going to use the qLTC property. So, okay, so first, given any resource state, I can just write down a circuit that's like quite small to prepare the resource state. If it's like, you know, you can think of this if this resource state is like, you know, like CCZ or something. So, and all it is I take the circuit that prepares the unencoded version of the state, and I just run the encoding circuit of my quantum code. This isn't fault tolerant, but I can do it. And the trick is that we're going to simulate this circuit such that it only encounters an error with constant probability. So we're going to take kind of some of these concatenated code schemes from the 90s, and we're going to simulate this circuit. That is, that we're going to replace all the operations here with concatenated code operations. All our qubits are going to be replaced by these concatenated codes, such that that this only fails with constant probability. And at the end, then we're going to unencode from the concatenated code so that we're left with a state that is a not too damaged code state of our locally testable code, quantum locally testable code, with constant probability. And roughly, we only need to pick a small number of layers of concatenation, so this gives us this low cost again. But there's a problem, which is that whenever this gadget blows up, we don't really have any control over what the state is at the end. So we need to ensure that our states don't have too many errors applied on top of them before we proceed with applying more gates, which is just going to spread this error further. So this I like to call logical leakage, because there's kind of a very similar phenomenon on the physical level with real qubits and real devices called leakage that has sort of very similar pathological properties where just the error just spreads. And this is where we're going to use the qLTC property. Roughly, we need to guarantee that a state that is output from this circuit here is in this green region here, that the error is not too large. The way we're going to do it is we're just going to measure the checks the code. And if the syndrome weight is too large, then we're just going to reject it. And if it's small enough, then we're going to accept. And there's going to be some false positives and false negatives. But the point is that as long as the errors in this syndrome measurement circuit are not too large, then any states that we end up actually accepting are going to be in the green region, and our error correction gadget is going to be able to maintain the state. We're not going to let any leaked states into the computation. So that's kind of that's the place where we use qLTC quite critically. So if we didn't have this, then actually we wouldn't be able to achieve anywhere near linear log. We'd be actually at like log squared, which is quite a bit larger. And then so finally, we had like a lot of moving parts here. And so now I need to tell you how to assemble them all together to like give a final threshold theorem. And so this is kind of a little bit about a proof technique. So roughly, we have all these gadgets that they're doing all these gates. And as long as not too many of certain subsets of gates are contain an error, then we can guarantee that the gadget succeeds. That is, it takes some good input state to some good output state under some particular definition. And what I'm going to call the support of the fault set of faulty gates in the gadget, I'm going to call it the fault path. And this is just some subset of gates. And then we're going to have these what we call bad sets of gates, sort of that as long as the set of faulty locations doesn't contain one of these bad sets, we can prove correctness. And so we call such fault paths good. And our noise model, the precise notion that we mean of local noise is what we call local stochastic noise. And this is just that for any given subset of gates, the probability that the fault path contains that subset is exponentially small in that subset size. And so what we can do is we can associate these set families of bad sets to a polynomial that we call the weighted numerator polynomial for this family. And it's just counts the number of elements of each size. And what we can do is just give a union bound for the probability that the fault path isn't good. That is, that it contains one of these bad fault paths, just by evaluating the weighted numerator at this parameter epsilon here. Okay, that sounds kind of trivial. But the point is that we have now polynomials that we can multiply and add. And in fact, we can even compose them. So addition is kind of very straightforward. This is just a standard union bound. But multiplication is kind of something that's a bit more interesting. In the fact that this model here, this is not independent noise. And you need, in order to prove, for example, thresholds against coherent noise and things like this, you need to be able to prove thresholds against kind of a local stochastic noise model. And so this recovers sort of this property that we really like about independent noise models, which is that if I have two different locations and I ask what's the probability that they both fail, ideally it'd be p squared if the probability that each individual one fails with probability p. And I'd also like this to be true of my gadgets themselves, right? If I have two gadgets, maybe it's my state injection gadgets or something like this, and they each fail with some probability, that I can bound the probability that both of them fail at once. And so that's what multiplication gives us. there's also this composition of polynomials, which we use actually quite critically in the threshold amplification step, where we can do kind of recursive simulation, kind of like think of like concatenation as in the 90s, but in a way that's a lot more black box than previously considered. So finally, just to summarize, we required this qLTC in order to get the very low overhead state preparation. We needed to construct a new magic state distillation scheme with sub-logarithmic spacetime overhead, which directly translated to the result. And we have this new composable fault tolerance tool to analyze our gadgets. And this is actually the first fault tolerance threshold theorem that we know of that actually uses magic state distillation. Surprisingly enough, probably due to the complexity of the analysis, this has actually just never been done before. And then this is our main result. Thanks.
We have plenty of time for questions. Any questions for Chris?
What is the constant space? Is a constant space equal?
No. We use a qLTC. And so these are very massive objects. So they use LPS expanders in that sense.
Any more questions? Okay, one question for the qLTC. You said you needed to be robust against a linear number. Do you think it would be possible to kind of go up to like maybe square root or something like this?
Sorry, say one more
So,
time.
so instead of having like this alpha n that you had, do you think it's somehow possible to kind of only have like maybe like a sublinear?
Yeah, certainly. So what we did is, just for simplicity, prove a decoder against adversarial noise, and then did this recursive simulation step. So kind of in code concatenation, kind of the thing that makes code concatenation so clean is that you can prove adversarial noise and then just convert it to stochastic, to a threshold against stochastic noise. So this is kind of what we did, just for simplicity, but it's very reasonable to expect that there exists kind of stochastic noise decoders that are single shot. That said, whenever you have sort of worse scaling, like very far off sublinear, then your block length blows up a little bit so you have to use larger blocks. And then the problem there is that then you have to serialize a bit more. So it will harm you, but it's something that you can certainly do. And yeah.
Okay, thanks. Okay, any more questions? Okay, if not, let's thank Chris again. We have a coffee break, and then we're back with the last speaker of today, which is Quinn.